Hello everyone, welcome to Stat 479 Lecture 23. This is the penultimate lecture for the course, and this is the third lecture where I go through the just kind of give you some hints on how to do the project. And so for the first couple of lectures focusing on the projects, we've kind of touched on tasks 1, 2, 3, and 4. And so today we're going to look at tasks 5, 6, and 7, which is really where we're starting to kind of analyze the data with some of our algorithms from class. And this is going to be very important. And there's a lot of kind of new ideas that I'll talk about here that are very specific to kind of working with real data that we haven't really touched on in the course. So in particular, I'll start by just talking about kind of training, test, and validation sets. And then I'll introduce this very cool concept that a number of you may have heard of, which is called k-fold cross validation, which is a really widely used and very it's a very simple but very useful technique for various different things, and I'll talk about those today. And then I'll talk also about training and test error, and this is probably one of the more important points to get across from the course, that you train on some data and then you test on a different set of data, and this is a really important kind of thing in statistics. And then I'll go back to the kind of the demo example that we saw. So that we've been working on for the first couple of lectures. So I'll just touch on sort of what what you could what sort of R commands and other things you might use through the demo example here. So we'll start with task 5, which is to pick algorithms from class. And so hopefully, based on what we've learned in the course, this should be one of the easier things to do, and there should be lots of different choices. So here we know that we have that yi is it's categorical, and then we have and so here we've got I equals 1 up to 988. So we have n equals 988, and then we have the xj's are so sorry, I guess the yi's, they're categorical, but more specifically, they're categorical with two categories. So I'll just refer to them as binary, whereas the xj's are categorical with three categories. Okay, and as I mentioned in the previous lecture, we need to do a good encoding of this, one-hot encoding, to make sure that we account for the fact that these are categorical. And so there's a number of different algorithms we could use here. So, the one that should probably first come to mind is if you think about generalized linear models. So I'll say algorithms / models. Remember that for every module that we learned, there was both a set of algorithms and models. So generalized linear model, and this is with the Bernoulli. So this is going to be with the Bernoulli length, because you have binary data. So that's kind of the choice that you would make here. That makes the most sense. And there's kind of lots of choices here. You could just look at main effects. And then, as I spoke about at the end of the previous lecture, pairwise interactions are also a perfectly reasonable thing to think about. Pairwise interactions. So I'm not going to demonstrate all of these. To be clear, kind of for this, this is kind of the most sort of open-ended part of the project, and there's a lot of different things you can try, and I'll certainly kind of the more things you try, the higher the grade you can expect on this on this project. And I'm only going to kind of demonstrate this on one. So I'm going to focus really on this one in today's lecture. But if I was to actually do the project, I would certainly go to pairwise interactions, and then we can also talk about regularization. So this is, lasso or, ridge. Perfectly reasonable. And then once again, we can have, the main effects, or the pairwise interactions. The pairwise interactions, and so this is this is certainly something else that we could consider. And so once again, and so we would use so the R functions that are going to be useful here are GLM and GLM net, and that's going to be useful. And I should also mention that you can also look at so the first two approaches cover modules 2 and 3, but then you can also look at graphical models. And that's if you you can ignore the response and learn graphical models for the XJ data. And you can do this either if you just fix, if you take all of the data, but you can also do this if you just looked at, say, the y=1 data. And so this is, so there's a lot of choices for what we could do with the data that we have here, and that's similarly going to be the case with any data set that you choose. Okay, so that's part 5 is sort of straightforward enough, and then it's good to kind of think about part 6 and 7 together, because when I talk about implementing an R, you should already have the idea of validation in your mind. So 6 is implement these algorithms, and I mean I'm talking about doing it in R, but you can certainly do it in any other language that you feel comfortable with. Implement algorithms in R, and then the validate algorithms. And the reason I'm going to talk about these together is because how you actually do your implementation is going to be influenced by how you choose to do the validation. So it's kind of very important to think about how you're going to do your validation while you're doing the implementation. And this is going to lead to the idea of before implementation, carefully think about splitting data into training, test, and validation sets, and I'll kind of talk a little bit about what those are shortly. Okay, so training, test, and validation sets. And the training and the test are going to be together, and I'll sort of talk about that shortly. But the key idea or principle is that a model, or I'll say okay, so the key kind of idea and principle, and this is the most important thing to probably take out of this lecture, and I mean, I would say just any kind of implementation of statistical methods you'll ever learn during your course is that a statistical model is only considered successful if it performs well on data it has never seen before. Um, so this is as simple an idea as it is. Like what this basically means is that you need data to train model. So to kind of and what that is we want to learn the parameters of the model. And this is what we kind of talked about in the class that we've spoken about in the class, that you start with your data, like your x and y or just your x's, and then you will learn some parameters from that data. And we talked about estimation and various other things like that. And to see if this model or say parameter estimates are good, you should use different data. Okay, so and I'm gonna kind of give you kind of an idea of why you want to do that. So I guess maybe now is probably a good time to start to talk about that. There's this very important kind of concept in statistics and machine learning about training error versus test error. So consider two data sets. So we have training, which is we'll call that X train, Y train, in this case, because we're talking about classification, and then test data, which is like X test and Y test. So you so to determine predictions for Y, or say to determine parameter estimates or predictions for Y, only use X train and Y train. So like, for example, you'd fit a GLM, lasso, or anything else. To determine parameter, so basically this is how you should kind of determine your model. But then you should so training error is how close is fitted Y to Y train. But you should point out that the method or algorithm has already observed Y train. So it should naturally fit Y-train well. And again, well here is in brackets because it kind of depends on what like what kind of model you use and so on. But because like in some sense you've actually seen all the labels for Y, you should kind of hope that your model predicts pretty well. So the testing error, which is substantially more important, we use the model from X train, Y train, and the data X test to predict Y test. And so we note that algorithm should not see Y test. So for example, if you're fitting like a regression model, you find so maybe I'll just write this out. So you start with X train, Y train. That might give you like a B hat, and then you're going to use the B hat and then X test, and that's going to kind of give you your prediction of Y test. And so that's kind of how this is going to work. So the B hat only depends on the training data, and so you don't actually see the test data. So why is this notion important? So just an example of training error versus test error. So let's just assume that our data here, this is our training data, sort of look like that, right? So this is what I'll put fewer data points in there so that the point's a bit clearer. We'll just have maybe 5 points, so it's gonna be like, okay, so say you have this is your training set, so this is your X and this is your Y. One thing I could do is I could certainly fit a model like this. Okay, so this is going to be model 1. Okay, but then on the other hand, I could also fit a model like this. Okay, this is model 2. So you can see that model 1 has 0 training error. And model 2 has higher training error. Has higher training error. But for new test data, model 2 will likely do better because model 1 overfits or fits the training data too well. Okay. And so just another kind of plot that you'll typically see is I guess this is model choice or complexity, and we'll talk about this as error. This is typically going to be what your training error looks like. So in some sense, your training error is going to kind of keep going down as you pick more kind of more complex models. So if you pick, you know, a model with more and more kind of parameters, you're typically going to do a lot better. But then what's going to happen to your test set, your test error is going to look something like this. Okay, and so this is like your test error. Okay, and you can see that, you know, there's this kind of point here where it's kind of an optimal thing to do, but then you start to kind of kick up, and that's because like here's where you're overfitting the model. And this is actually very connected to the bias variance trade-off for ridge regression or lasso from module 3. Kind of, you can imagine that the x-axis here is model choice or complexity is going to be basically something like 1 over lambda. So as lambda gets bigger, you're kind of getting a less complex model. So if you look at 1 over lambda getting kind of bigger or lambda getting smaller, you're getting a more and more complex model. So so that's kind of you know, you expect to see something like some behavior like this for regression. We actually kind of derived this bias variance trade-off. So so that's kind of just connecting this idea of training error and test error to the bias variance trade-off. Because what you really care about from a statistical point of view is how you perform on data that you've never seen before. So so yeah, so sorry about that. Yeah, so the main point out of this is that performance on test data much more important than training data. Okay, so you know, that's hopefully just a bit of a, you know, an explanation of what's going on. There's lots and lots of kind of notes on this. You can look up bias variance trade-off and various other, like if you look up training error, test error, you'll kind of see similar plots to this in various places. And this is kind of a very key like point in statistics. And so kind of what I don't want to see in the project, but what the mistake that a lot of people still make when they run statistical analyses is that they will you know, they'll run a model and then they'll kind of like look at how the performance is on the data that they've used to train and say, oh wow, our model does really well. And that's kind of not something that I want to see in your projects. I mean, you can certainly report the error that you see, and I will actually talk about that later for the specific example that we've been looking at, but like don't sort of use that as a way to justify that your algorithm has done well, because that, like, performing well on training data is not really something that's considered impressive, because you really want to be able to do well on data that you haven't seen before. It's the ability to generalize, which is a very key part of statistics. So just to illustrate, to explain kind of the, I guess, the different there's the training set, there's the test set, And there's also this third set, which we call the validation set. And the way you want to think about that is that the training plus test sets are used to determine the best algorithms. And the reason why you need both, like even though you're only going to train on kind of, on your training set, because you're kind of going to kind of compare various different algorithms on your test set, you still want to hold out some extra data that you kind of don't like, that you don't touch at all at any part of your process, because and that's going to be your validation set, because like when you keep kind of like touching the test set for doing for evaluating your methods, then you're going to kind of you're essentially going to like kind of start to overfit because of the fact that you've kept that all of your algorithms have kept seeing the data set over and over again. So so that's kind of a subtle but important point, that since you train many different models, that all involve test sets. Algorithms eventually see the test data. So therefore, also have a validation set that you don't touch until the very last step. The very last step when you have selected final model. And this is particularly important if you're going to run things like the lasso or ridge regression, because one of the key things is you have to choose the regularization parameter lambda, and there's many different ways to choose that. And so you kind of want to like make sure that you're not using the same data to choose the lambda as you are to do your validation, because you're kind of using like, you don't want to ever be sort of reusing data as part of your validation. So that's something kind of really important to keep in mind. So how you split that up kind of depends on, this is sort of a model choice. So a rule of thumb, you'll have train plus test will be 80%. And then validation 20%. So this is just so this is an arbitrary choice. So you can certainly make a different choice, and it's not wrong. It'll depend a little bit on how much data you have, because if you don't have very much data, maybe you don't want to have too large a validation set. Otherwise, you don't have enough data to train your model well. And so that's something that you need to choose. Okay, so now I'm going to talk about how we deal with the train plus test set. I should also mention that you typically choose these sets. Choose these sets randomly. What you want to make sure is that you don't, in some sense, that you get the same distribution for the training, test, and validation sets. So for training, test, and validation sets. Okay, and this is kind of really important. So, for example, I have some data here where we have responses of ones and zeros. You kind of want to make sure that the distributions of ones and zeros is roughly the same for the training, test, and validation sets, because if they're not, you might end up with a training set full of like ones and a test set full of zeros, or a validation set full of zeros, and that's not going to be very useful when you're fitting your model. So just that's why you choose that randomly, but more importantly, just make sure you kind of get the same distribution across the different data sets. Okay, and so I'm going to now talk about this, it's a very useful technique, which is k-fold cross-validation. So this is something that a number of you may have heard of already, and it's so widely used that a lot of programs actually have cross validation built into them, because it's known that this is so widely used. So the basic idea is that you have train plus test set, and so this might be like 80% of your data, because you hold out 20% for validation. And so what's kind of interesting about k-fold cross validation is you can think about it as the whole, like, your whole data at different times could act as both a training set and a test set at different points. So the way it works is that you pick a k between I guess 1 and n, and then you divide the data, and this doesn't include the validation set, so everything except the validation set, would divide the data into k folds that are even. So obviously, like, you may not be able to make it perfectly even, but just try to get it as even as possible. So if your k equals 2, and if you have an odd number of samples, you can obviously quite easily just make that, like, you can pick, if it's let's say, like, 151 samples, you can pick 76 in one and 75 in the other. So this shouldn't be too big a deal. And once again, make sure the distribution is the same across the k folds. And so the basic idea is that you train on k minus 1 of the folds, and then you test on the other fold. So it's not especially, like, it's not, the idea isn't especially deep, but it's still kind of a very useful idea. And then you can repeat for all k folds. So basically, you can ensure that each of the k folds is going to be the test set at some point. So you're going to actually get k different models that are hopefully very different, very similar. So you'll get k different models. Hopefully difference is small. Difference in models is small. And this is actually related to this is a good stability validation. because if you kind of split your data up and get very different models, when you can, depending on how you split the data up, that's kind of telling you that there's something kind of unstable about your data that you need to worry about. So the idea is that you will get k different models, but hopefully they're very similar. So which of the k you choose shouldn't make a huge difference. Okay, and so one key question is how to choose k. And then this is going to depend on your data size. So for a smaller n, and you make k larger to ensure training set is big enough. So just as a rough rule of thumb, I mean, if as a minimum, you kind of want like the training set to be roughly 20. So, if you've got a really small data set with say n equals 20, you kind of want to choose k equal to n. So, so if n's small, choose k equals n. And this is what's called like leave one out analysis. Leave one out, or leave one out cross validation, where you're training on every sample bar one, and then you're testing on that one sample that you haven't trained on, and then you repeat this n times. And this is kind of again, as I mentioned, there's going to be a lot of various design choices that you make when you're doing this analysis, and as long as you justify your choice of k, it doesn't really matter too much what it is. Okay, so that's kind of a useful technique to know and to do. And so now I've kind of spoken enough, so I'll talk a little bit about the specific example that we have, or this is the demo example. And once again, I mean, I'm gonna only spend about 15 or 20 minutes on this, so I can't go through what I would expect you guys to be able to go through with the project, where you have a lot more time, and you're potentially working in groups as well. So so I guess what I'm trying to say is, like, don't feel that if you just do what I do in the lecture for your data set, that's going to be enough to get a really good grade. This is just showing you just a taste of what's required. So have our code lecture 23 in front of you here. So there's a combination here of commands and also outputs, so that you can look at that just to kind of see. So the first thing is that we wanted to split into training and test or validation set. Okay, and so here what I've done is I basically just said that 800 is the training plus test size, and then 188 is the validation size. Hey, one thing that's a little annoying and a bit misleading here, which I regret, is that I've called validation test here, but this is really something that I'm not going to touch until I've got my final algorithm. And so this is this is the first thing we do, and that's the first set of commands that you'll see. And I've kind of followed the 80-20 rule roughly. The next thing we need to do is to convert x's to factors. And this is where we use the factor command. And note that if you look at the code, I'm only looking at the training data. So what you'll notice is for the next part of the of what we do, I'm not actually going to touch the test or validation data at all. I'm only going to touch the 800 samples that correspond to the training data, or the training plus test data. And then the next thing to do is to just run the GLM function, and I'm just gonna, because we're trying to kind of pack things into the lecture, I'm just gonna pick k equals 1 here. So so one pass of the data, just to kind of to keep things simple. And then so you can see that I've run the GLM function on with the y, the training sets on the various factors, and then I've used the summary function, which is a very useful function, which just kind of gives you a sense of which features are relevant. So I guess one thing to note here is that so the highly relevant features according to the GLM are we have or X, we can kind of see what's most significant based on how many stars there are. So I'm only going to list the ones that are 3 stars. So the number of stars refers to the significance level. So if it's rejecting at just a 0.05 level, then that's going to get 1 star. If it's rejecting at a 0.005 level, that's going to get 2 stars. And if it's rejecting at a 0.0005 level, then that's going to get 3 stars. And so I'm only going to put down the features that got 3 stars in this case. So we have x1 equals 2 is 1. We have x2 equals 3. So these are binary features, remember? So this is just saying that if you look at if the first position has the second parent, that's a relevant feature. The other thing to note is the sign of these estimates. So you can see that some are positive and some are negative. So I'll put down positive, and x2 equals 3 is in fact negative. So that's saying that if the coefficient is negative, it's saying that it negatively influences the overall functionality. The other ones are, if you read down them, you have x4 equals 3, and that's a negative feature. And then you have x5 equals 2. That's a positive feature. X5 equals 3. That's a positive feature. And note that we don't actually see any of them equal to 1, and that kind of suggests that x5 equals 1 is a highly negative feature. And then you have x7 equals 3, which is a negative feature. So these are just kind of if we just look at the data and look at the summary of the coefficients, this is telling us that these are sort of the most relevant positions and the corresponding parents that sit in these positions in terms of predicting functionality. So positive means that they are more likely to increase functionality if you see that parent in that position, and negative means that they're more likely to decrease functionality if you see that parent in that position. And there's various things like AIC and deviance, and if you have questions, I can talk to you about what those are, but they're kind of a measure of how well you fit the data. So then the other thing to kind of think about is that how well does model predict data? And this is really what I'm going to talk about first, and what's in the code that you'll see is the training error. So here you'll notice that I'm comparing, so we're going to compare fitted y's to the y training that we see. So this is where we use the GLM dollar fitted values. So dollar is a very useful thing for dealing with these data frames that kind of accesses specific elements of the data frames. One thing also to note is we have binary data, but what you always predict when you do logistic regression is a probability of being 1. So you're going to get a number between 0 and 1. So for binary data, need a probability threshold. And I'd say, so what I choose here and what you'll see is that 0.5 is most obvious choice. It may not be the right choice, by the way. It's just that, if your data is reasonably balanced, it's not a bad way to kind of choose a threshold. But, sometimes you might want to look at your data and maybe a choice like 0.3 or 0.8 is actually a much better choice for the threshold. So that, to keep things simple, we're just going to choose 0.5. And then the training error I'm going to report here is just the misclassification error. And that just counts the number of places where there's a disagreement between the y train and the y fitted values when you threshold at this 0.5 value. And so what we get here is about 18%, and that's not too bad. The other thing to keep in mind here is that for binary data, you often care about the error type. So, sometimes if you incorrectly label something as positive, that's a very, bad thing compared to labeling something as negative. So often what, people want to see for binary data is something more like a table, which I've also constructed, as you can see later on. And this is just the so if you look at the predicted label, you can have here a 1 or a 0, and then the true label. That's a 1 or a 0, and I did these calculations to see where we're kind of making the errors. So this kind of gives you all the information you need to determine the different types of errors that you're making here. The next thing, and this is the most important thing, which is the test or validation error. Because as I mentioned, there's no real value in just the training error, because there's many methods that have training errors that are 0 or very close to 0. And that doesn't mean that you're doing well on new data. And so this is where the test error is really important. And so you can see that I have code for that as well. So this is where I use so we use the predict function in R. And note here again that only use X test, don't use Y test at all. So we're gonna use the trained model from the training data, and this is stored. This is something that I already stored, and then we're going to use the X test with these new beta values. So in some sense, we're running a GLM, which means that we have beta values for the different factors. And so we're going to use those beta values along with these new sort of factors that we have here. And once again, we use a threshold of 0.5, and you can actually see here that the test error is pretty good. It's in fact lower than the training error. We get about 16.5% for the test error. So therefore, our method has good test error. That sort of suggests also that we're not overfitting the data. So this is kind of just a very kind of quick demo of what you might do, on this demo data set. But there's still kind of lots of things that I haven't spoken about yet, which I'll kind of just touch on briefly. So other issues. So the first thing that I touched on right at the beginning of the lecture was we should try including pairwise interactions. So if I was doing this project, the next step I would do would be to try pairwise interactions, because as I mentioned, we do have enough data to look at pairwise interactions. And there are, the question then becomes, which, so this significantly increases the number of features. Okay, and so this is where model selection and overfitting really come in even more, because when you only include main effects, it's unlikely that you're going to overfit the data, because there's only 16 features there, so it's unlikely that you're going to overfit the data, and we certainly saw that we didn't overfit the data with that. But when you start increasing the number of features a lot, which will happen once you have pairwise interactions, that's then you run the risk of overfitting. So overfitting becomes a potential issue if you include interactions, if you include pairwise interactions. Okay. The next thing that I wanted to touch on is that we could or probably should also try lasso or ridge regression, and then you can say with both main effects and interactions. And that's that's certainly something that's worth trying. And then one key challenge here is how do we choose lambda? And this is something that is a very kind of open and challenging question. We have the theoretical results when we assume a model, but in practice, we don't really expect our data to follow our model exactly. And so this is where the importance of the validation set and the training test set is really important. So, most widely used approach is k-fold cross-validation. So I've mentioned that validation can be used, k-fold cross-validation can be used as a way to determine if your method is accurate on some unseen data. But but it can also be a good way to choose parameters of your model that you need to tune. So the way that works is that you choose so choose a lambda that minimizes prediction error. Prediction error calculated by k-fold cross-validation. Okay, and so you shouldn't touch the validation set when you're doing this, because otherwise you're going to, have that sort of overfitting issue that I mentioned earlier. But in some sense, what k-fold cross-validation gives you is it gives you a way to estimate prediction error, where you train on a set and then predict on a different set. And so one thing you'd say is that, okay, for different choices of lambda, you might select the lambda to be a grid of maybe 5 or 10 or 50 different values. You could choose a lambda that minimizes that minimizes this prediction error, and that's a perfectly reasonable choice of lambda. So and the one thing to keep in mind here and to be careful of is make sure choice of lambda does not depend on data in the validation set. So this was not an issue for the GLM model because we didn't have to choose any tuning parameters. So I didn't really need to sort of tune anything with the GLM. It just kind of runs itself. But here we have these tuning parameters lambda. And so this is where the idea of train test, like the train test plus validation set's really important, because you want to make sure that you in your choice of lambda, you don't look at, and like when you determine whether your lasso or ridge regression or whatever method you use is good, there's gonna that fitted model is going to have a choice of lambda in it somewhere, and you don't want that choice of lambda to depend on any data that you're going to validate on, because otherwise you're kind of cheating a little bit by using that data to in your algorithm. And so you don't want, so the kind of the key message out of all of this is that you don't want any validation data used to determine you don't want any choice of any validation data used to determine the model. Otherwise you're, in some sense, you're kind of data snooping or cheating, and that's something that you want to avoid. But and as I mentioned, as simple as it is to say that, this is still a mistake that's very, very commonly made in practice, and people kind of get very misleading results because of it. Okay, so that's kind of that's it for the demonstration of how this works, and I've given you a few hints at the end to kind of think about. So as I mentioned, because I'm kind of trying to just get you started with things, and I've condensed the main point, and I've only focused on the GLM model with main effects, but as I mentioned, interactions and various other things could come into play, and that's something that I expect you to look into for your project where you have kind of a lot more time. And so again, as you can see from what I did, there's lots and lots of different choices that need to be made, and this is always the case when you're dealing with real data and developing algorithms for real data. And so make sure, there's not necessarily a right or wrong choice here, but just make sure that you explain the choices that you make. Okay, so that's it for today, and then we have just one more lecture to go where I'll just kind of wrap up what's expected on the project. So, and that'll focus on tasks 8 and 9. Okay, thanks very much.